Is the data spatially autocorrelated? Let's figure out.
At the second lesson of the third geostatistics course, we created the script for the omnidirectional semivariogram cloud, and that's the script that we are going to use now. Then go here to structural analysis and open the first script, semivariogram cloud, double click to open, select the layer that is going to be any of these two layers. I'm going to use this one. Then the parameter is going to be the log 10 because we are going to use the transform data. And in order to know what is the cutoff, what we are going to do is calculate the distance with this tool over here. Click in meters is good. Then we are going to put at the first dock, at the first station, and we are going to select the longest distance. And we are going to select the longest distance. The longest distance is going to be this one. Then click over here, then select this one, Control C, and then we are going to paste this distance here at the structural analysis over here, at the cutoff, Control C, Control V. Here is the distance. Then the parameter, data set, the layer, the parameter is going to be this one, and for the label X is going to be lag distance. For the label Y is going to be the semi-variance of the log 10 for the air quality index. Title of the graph is going to be Omnidirectional Semivariogram Cloud. And for the subtitle is going to be Transform log 10. Then we and double click to open. Let's go to make this screen bigger. We did the omnidirectional semivariogram cloud for all the extension. It means that we have here all the possible pair of samples, okay? Because we took from, let me close this one here, because we took from here to here and it takes all the data set, okay? Then also the omnidirectional semivariogram cloud, it is very interesting to identify any trend on the data. As you can see over here, the data points are distributed pretty randomly and we cannot see any trend on the cloud of points. Also, the graph is really good to identify outliers. In this case, the outliers are going to be all these data points that are out of the main cloud of points, right? If we are considering that the main cloud of points is all this area, then all these dots over here are going to be considered outliers. However, as the density of the points, for example, over here, it's very, very low compared with the density of points over here, these outliers are not going to affect the experimental semivariogram. The same is going to happen with these outliers over here. The density over here is not that much compared with the density that we have over here. But in this case, as you can see, the density here is pretty poor, okay? And here we have a lot of points also. Maybe in this case is going to affect. But as this area of the graph is about the uncorrelated data, we are not really care about this area of the graph. The most important thing is the correlated area that is going to be this section of the graph over here approximately. We are going to see this information more clear with the next script that is about the omnidirectional experimental semivariogram. Remember that that script was created at the fourth lesson of the third geostatistics course, and that's the script that we are going to use now. Then to do that one, we are going to select the number 11. With this script, we can see also the variance. Then we are going to select any of these two data sets. The parameter is going to be this one. The cutoff, we are going to add the same as here, because first we want to do for option, then later we are going to be more accurate, but that's the first approximation. Then for this one is going to be the same label here, paste. This one is going to be the same, copy, paste. The title of the graph is going to be the omnidirectional experimental semivariogram, copy, paste, but I'm going to make some modifications here. Omnidirectional experimental semivariogram, and I'm going to remove this one. And for the subtitle is going to be the same, copy and paste. For the lag distance, we are going to take this distance, copy the cutoff, then take the calculator and over here, and we are going to divide that one between 10 because we want to have at least 10 lags. Then we are going to copy this one, select all, copy, and we are going to use this one as lag distance. Paste. Remember that this is the first approximation. Later we are going to be more accurate, okay? Then run. And let's go to move over here, double click to open. Let's go to make this screen bigger. And that's it. Here we have the semi-variance for the log 10 for the air quality index. Here we have the lag distance in meters. This value over here is this, the semi-variance or the variance for the data set. And here we have the number of pairs for each lag, okay? Value cannot see really well. If you go here to the script, you can go up a little bit. And you are going to see that the first lag has 1,904 pair of samples, okay? And as this number is quite big, we can say that the values are representative, okay? Here we have also almost 3,000, 2,500, 2,000 again. And what we can see here is that the data is not showing an exponential trend. That is very important because that is indicative that the data is stationary. Because the data goes up, then reach this point, go down, go up, go down. Okay, we don't have an exponential trend. Also, what we can see is that the data get stabilized approximately where the variance is located, because go here up, go here up, and then go down, okay? And that's very important because also is indicating the presence of a structure, okay? And it is very important to have a structure, because if we don't have a structure, it means that the data is not spatially autocorrelated, and we need that one in order to apply the Kriging interpolation. At the end, what we want is to have a very small nugget effect compared with the partial seal. And as you can see in this case, the partial seal is going to be more or less from here to over here. We are going to have all this one as a partial seal, and the nugget effect, if we have something, is going to be very, very small. And that's indicative of a good structure of the data. Then the next approximation, we can use the same graph, but instead to use all the extension, what we're just until here. We are going to use this distance as a cutoff, and we are going to make the representation of the graph until here, because as we can see, the correlated data is in this section of the graph. Then we are not interested to use this data, because what we want is to fit the model just in the data that is showing correlation. And as you can see, we are going to reach the seal approximately on this area. Then let's go to create the next graph. And for this one, we are going to use the script number 10, because we know already what is the variance. Double click to open. It's going to be this one. The parameter is log 10 for the air quality index. The cutoff, as I said previously, we are going to use this distance. then it's going to be 3, 1, 2, 1, 2, 3, 5 zeros. For the lag distance, I'm going to use 30,000. Is the cutoff divided by 10. And here is going to be the same labels. Copy, paste over here. Also, this one is going to be the same. Copy, paste. This one is the same. Copy, paste. And for the subtitle is the same. Copy and paste. And let's go to run this script. And double click to open. And let's go to make this screen bigger. And then we are going to use this data to fit the model. Okay. As you can see, every lag distance has less pair of samples because now the lag distance is shorter as before, right? Here we have 1,900. Here almost we have 3,000, 2,500. But now every lag distance has less pair of samples, okay? But anyway, with 500, it's really good. Even 235 is really good. Any number that is higher than 100, it's pretty representative. And in this case, with this lag distance, the pair of samples that we have for each lag is really good. And it's representative of the data, okay? Each lag distance is representative of the data. And again, here we can see how the data is growing and then reach the seal over here and then stabilize, okay? It's okay. It is indicating the stationarity of the data. Now, the next step is to fit the model in this data set. And to do that one, we are going to use the scripts that we created at the lesson 5 of the third geostatistics course. Then we are going to go here again. And we are going to select one of these ones. It is the number 19. Then we are going to add here, no, not this layer, this one. Parameter is going to be log 10 for the air quality distance, for the air quality index. Here the cutoff is going to be this value. The lag distance is going to be 30,000. The seal is going to be approximately, okay, because these values doesn't have to be exactly. We can add the seal as 0.06, but it's not really the seal, it's the partial seal, okay? 0.07. This one is wrong. Here has to say partial seal. Also, the model first, we can try the spherical one. Again, this is an approximation. The range, we can see the range over here approximately is going to be maybe 250,000. Just an approximation. The nugget, it could be this one. The label for X, we are going to copy this one here. Copy and paste over here. The Y the same. Copy, paste. Title of the graph is going to be Theoretical Spherical Semivariogram Model. And subtitle is going to be the same as this one. Copy and paste. Or what we can do here is to put the spherical as a subtitle. Cut and paste. Spherical. That's up to you, right? Then remove this one here, theoretical semivariogram model, and okay. And with this script, the model is going to be fit on the data automatically, okay? Then we can run. And here we have the values for the model, okay? Here at the beginning, we have the nugget effect. Then we have the partial seal. And here we have the range for the spherical model, okay? Then we can open this one, make the screen bigger, and that's how the software fit the model automatically on the data. Now, if we want to change for a different model, for an exponential one, for example, exponential, then here we can change for exponential also. And let's go to run to see how the software fit the model. Double click to open, and this one is the result. And also we can try for the Gaussian one. Here Gaussian, and let's go to change here for Gaussian. And let's go to run. Double click to open, and this one is the result. As you can see, the Gaussian doesn't look really well. Maybe the best result is going to be between the spherical and the exponential. Then we can do here the cross-validation to see what is the ones that provides the better root mean square error. I know there are a lot of scripts that we created at the third year statistic course, and all the scripts, because the video is going to be very long, right? And all these scripts are explained in that lessons. Also, we cannot be talking about what is the best way to calculate the lag distance, because it's going to take a lot of time. All these things are explained already at the third year statistic course, that it's about the structural analysis. Also, we have scripts that can calculate what is the best semivariogram model automatically. Also, we can fit the model manually, but we cannot work on all that stuff because